Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So I just want to pick up from where I was last day. So last day I was talking about the language of a Turing machine, and I gave you a formal definition based on instantaneous descriptions of a Turing machine. And then at the end of class last day, I defined two sets of languages. I described what are so-called Turing recognizable or recursively enumerable languages. These are the languages for which if I give you some language, say L, and I tell you that it belongs to RE, recursively enumerable or Turing recognizable, usually I'll abbreviate this by saying recognizable. So if I tell you, okay, there's some language that's in this set, what I can guarantee for you is there's some Turing machine where for every W in that language, there's going to be a Turing machine that indeed can recognize each string in that language. But as I told you, a Turing machine doesn't just only accept and reject. There's always the possibility that it could reject, or it may never reject or accept. It might loop forever. So these languages are what we call the recognizable ones, or Turing recognizable languages. Is if there's some Turing machine where every time I can tell you, oh yeah, look, this language, there is a Turing machine that can always tell me the strings in that language, but nothing else. It may be the case that it may not even halt, for example, if I give you a string that's not in the language. Then there's this other set, the set of all so-called, these are the recursive languages. So this one imposes the additional property that the Turing machine must halt on all inputs. So remember, that means that we're going to be considering Turing machines we call deciders. And if I could give you a Turing machine that could tell you whether, if I have some language L, it'd be able to tell me, so it either will accept or it will reject. But there's no middle. There's going to be no possibility that this is going to loop on infinitely forever and ever. That's not happening. So if there's a Turing machine that exists that is capable of this, we say it belongs to R, the recursive languages or Turing decidable languages. I'll abbreviate this as saying the decidable languages, which will have its natural intuition here in one moment. Now, depending on how much time we have in the coming lectures, I will hopefully be able to justify this statement for you. If not, I want to mention this to you, is that all recursive languages are recursively enumerable, but the other way around isn't true. So that means that you got to think of the recursively enumerable languages as a superset of the recursive languages. So just keep that in mind, and it does make sense. Remember, here I'm imposing an extra criteria that it always has to halt, right? But it most certainly will tell you if W is in that language, right? Which, that's all I need to be recognizable. So I want to touch on something I was poking at last day, and I want to kind of peel that open to talk about it, like I'm enjoying an epic mango or something, or whatever your favorite fruit or vegetable or whatever it may be. Something that I'm peeling open to talk about. I don't know, an onion? They have layers. The point here is that when we talk about a decider, remember, that's a Turing machine, like I said, that always will halt. If we have that, then we can tell you either the string is the input, W, is in the language or it is not in the language. But that also means that our Turing machine always has to halt after some finite number of moves, right? But I also want to bring up something. Say, for example, in a course like CS340 or any analysis of algorithms class, you may be told that an algorithm, like this is a good working definition, you may say an algorithm is an unambiguous step-by-step procedure that takes input from a problem instance and it produces output. And we say that the algorithm solves the problem if it produces correct output for every instance of that problem, correct? Well, doesn't this notion of a decider seem rather similar to this? In fact, it exactly matches it if we're talking about a decision problem, correct? So this brings me back to something I talked about at the beginning of the course when I talked about decision problems, right? So a decider is actually, like, it matches this intuitive notion of an algorithm. that you may have used in previous courses, or you still may use, like people like me. We often will use this conception of an algorithm. So if you think about it that way, if I have some algorithm in this sense, and it exists that solves some problem. Now remember, I told you that there's a connection between problems and languages. The connection is direct if we're talking about decision problems. They're one and the same. There's an equivalency. Then we say that that problem is decidable. So just to be clear, so if I give you some decision problem, remember, we can think about all sorts of different kinds of questions. I'll be talking more about decision problems later on, but most certainly we gave an example at the beginning of the course asking if a number was prime or not, right? So I give you some prime number and I ask you, is it prime or not? So either, yes, the encoding of that number is in fact a prime number, or no, it isn't, right? It's in the language or it isn't in the language. So just to be clear, if I tell you there's some algorithm that solves this problem, tests if indeed it is a prime number, yes, no, then we could say that that problem is decidable. So we normally use this notion of a decidable problem more broadly in computer science, because decision problems, even though some problems don't really fit exactly into that notion in the exact way, there's very easy ways to transform them into things that look like decision problems. So just as an example, if I give you an optimization problem. So formally, an optimization problem can be thought of as a collection of decisions. So just as an example, if I give you, say some problem like, you may be familiar with something like computing a minimum spanning tree, which is a problem that has efficient algorithms for it. You can always cast computing determining the existence of a minimum spanning tree with a given total cost as a question. You can ask, does there exist a spanning tree whose total cost is at most some value, say k? And you can answer yes or no. When you think about it that way, then you could solve an optimization problem by asking a series of questions. So there's a couple different ways. If you just wanted to run it in finite time, you could just simply ask the question starting at 1 and work your way up till you find the smallest possible answer for your value k. Or you could just use binary search and you could guess what the optimal is. So there's a lot of ways you could think about problems in terms of decision problems. And you could also think about this even with function-based problems. There's some function-based problems that, remember, we had Turing machines that would take in input and then they would produce output, correct? So our transducers. So conceivably, function-based problems like that could be thought of like transducers, right? So do you see that this notion of an algorithm seems to be pretty natural and flexible if we think of an algorithm like a Turing machine algorithm, as in an algorithm that I describe using some Turing machine? So that brings me to talking about something I would consider a big deal. This is the big deal. I want you to really think about it. It brings me to talking about what is called the Church-Turing Thesis. So this is named after Alonzo Church and Alan Turing, who had different conceptions of what computation means. So before we had logicians and mathematicians thinking about these problems in the 30s in particular, but there were people like Kurt Gödel and them that were thinking about fundamental questions about, okay, well, there's all these, I'll talk more about it, I'll try to give you the story when we start talking about undecidability, but when I talk about this, up to the point in the early 20th century, there wasn't really a formal definition of what an algorithm is. There really wasn't. People have been studying procedures and what we call informally an algorithm for many years. Like there's even ancient algorithms dating all the way back long before Turing or Alonzo Church. But there was not a formal notion of what an algorithm was. So there are a lot of people that had ideas of what it means to be so-called effectively computable. So it just means some procedure just like what you think about in a course like CS340, for example. Or you think of some computable function, something that computes based on numbers, some output. Kind of like what I talked about when I talked about a transducer, and I told you that, oh, Alan Turing was interested in functions like these. So up until that point, people were like, okay, well, what does it mean to compute something in a sense that we might talk about it today? So there was a proposal of this following idea, and it's only gotten stronger over the years. It is not a statement of mathematical fact. It is a hypothesis or thesis. So it is not a proven theorem. It is not really, you couldn't really, there's ways of thinking about it, but it's most certainly not meant to be like a mathematical statement. So it's not proven in that sense. It is something more empirical. In fact, it's just a statement in general, and it boils down to this. So I'm going to first give you a plain language description of what the Church-Turing Thesis can be, and a couple of equivalent ways you could think of this. So in plain language, so I mean just in layman, when I tell you algorithmic, if I talk about algorithmically computable, means computable by some algorithm. This is equivalent to me saying this means computable by Turing machine. So this is kind of the big idea here. So if I tell you, okay, there exists some algorithm that solves a problem, what I'm telling you is that there is an algorithm that I could describe as like a Turing machine. That's where I'm going with this. So in prior lectures, I was trying to motivate that we can do all sorts of different things with Turing machines. So the Church-Turing Thesis in plain language is this, but here's a couple of different ways. So I'm going to first give you one way of thinking about it. This is from Sipser. So the intuitive notion of algorithm, so like I've talked about or you've seen before in prior CS classes, equals Turing machine algorithms. This is as stated by Sipser. So that's one way you could think about this. So whatever I describe to you, some algorithm, whether it be, say for example, I'll talk about minimum spanning trees a moment ago, like Prim's algorithm. What I'm saying to you is that there is a Turing machine that I can use to encode Prim's algorithm. And I could do this for any algorithm in the sense that you might have talked about in a prior course, just like ones I'm describing right here. But here's the interesting equivalent way you could think about this. And now this, I really want you to just try to absorb this. Consider problem pi. I'm going to give it a name. I'll call it pi. Not the delicious kind. If there is no Turing machine that decides pi, then there is no algorithm. There is no algorithm that solves pi. So just to reiterate this, so if I consider some problem pi, if there is no Turing machine that decides pi, then there is no algorithm that solves pi. That's a lot to take in. So if I'm telling you that there is no Turing machine, so no decider for that problem, then there most certainly is not going to be any algorithm that solves it. That's something I want you to think about, because I'm going to just try to, because this is a pretty bold claim, right? Like, this is very bold for me to say, right? I don't want to just you to be like, yeah, just accept this. For you, I want you to really just think about this carefully. So think back to all the years you've probably been studying computer science at this point, and say to yourself, okay, well, the dots seem to be kind of connecting here. But Dan, you maybe should try to like tell me maybe why a lot of people think this thesis seems to hold. Well, historically speaking, Alonzo Church, he had what is so-called the lambda calculus, and that was Church's conception of what it means to be computable. Later, Turing came along. This is not that long after. Turing came along and he proposed what we now call Turing machines, so his automatic machines. And Turing's conception of a Turing machine, it's kind of weird for me to say that. It is indeed a mechanical or algorithmic description of how we compute to solve problems. So often when people think about the Church-Turing thesis, what it is effectively telling you is that the standard model for computation and the questions of does there exist an algorithm or not, it's fundamentally attached to a Turing machine. But here's the interesting fact I need to tell you, is that when we talk about the Church-Turing thesis, there are many, like remember I told you the other day that there's not just one Turing machine conception. There's several different ways you can equivalently define the Turing machine. I'm going to show you some of those today. Where when I say this statement, I'm really saying anything that's equivalent as well to a Turing machine. So you could have easily have said to me, hey, look, instead of writing Turing machine there, I could have wrote lambda calculus. I could have written Turing machine that has the ability to have a stay option. I could have said your computer, a laptop, or your desktop. These are all things that I could prove to you are actually equivalent to a Turing machine. Which is very, very strange at the first time you hear this, right? Because it's just, Turing machine is just this tape, right? You tape, you read the head, you move it, you write letters to the thing. But so that brings me to talking about really kind of the bits and pieces to this that I really just want to make sure it's clear to you of why people affirm this thesis. So its evidence is from that. So what I'm going to do is I'm just going to give you just an idea of why people typically adopt this. So its evidence is from that every realistic model of computation that has been discovered or presented thus far has been shown to be equivalent to a Turing machine. So I'll go into more detail about what I mean by that in a little bit. So I'll actually be showing you some examples of how you can go about this. So just to give you an example, so for those that have taken, say, a class like CS 340 or analysis of algorithms class, question, is there a possibility to turn Church-Turing thesis to a theorem? Now, like I said, that isn't technically a statement that is a mathematical statement. You could think of it as a theory or a hypothesis. It's more of you can think of it more in a broader scientific way. However, I must stress that you're going to see that even though that isn't really a mathematically proven statement, there are most certainly models of computation that basically model our computers that are in fact equivalent to a Turing machine. Or if you think about more broadly, like a stored program computer, there's other equivalents for those based on Turing machines. So just as an example, you may have heard of something called the random access machine model. So you might know this as the RAM model. So this is one that's fundamental to most algorithm researchers. They typically will take this, and then that's basically what builds all your analysis of algorithms techniques that you're familiar with. So for example, when somebody presents you, for example, I talked about Prim's algorithm. Somebody might present that to you in pseudocode, and they say, okay, well, let's analyze the running time of the algorithm. And they give you some rules to count the instructions. Those rules are based on this model. And I could tell you this model, again, equivalent to a Turing machine. And that model is fundamentally a sequential that's the model we use for sequential computing, right? Now, I must stress that literally when you adopt a different model, there's different ways we can measure the complexity of an algorithm based on that model. There's often connections between them. I'm not going to talk so much about that quite yet. I want to touch on that a little later. But the big idea here is that you might say, oh, well, I don't really use a Turing machine when I analyze algorithms, but you will certainly use this at some point. Now, if you don't know exactly how the RAM model exactly works, if you were to look up and learn a little bit more about this model, I'm not going to have time to talk about it, but it's very similar to assembly. So you can look at this very much like, okay, well, I have my assembly program. Just if you're thinking more from a system standpoint, you can have your assembly that you used for the machine code of a physical computer. With a RAM model, for example, you may have something that's akin to this, and then you could build your more higher level descriptions of algorithms on this side. But there is a direct connection so that I can go from a Turing machine to this RAM model for an arbitrary RAM. And the same idea here, I have my assembly code. I may have some compiler that translates my higher level programming code from this assembly to some higher level or vice versa. So that just in the same way, when you talk about, oh yeah, no, look, when I implement a computer program in a programming language like C++ or in Java or another language, you often obscure or ignore the lower level details. Just in the same way, you can think about how we analyze and describe algorithms in a higher level, like with pseudocode, which, of course, you can go to lower levels of granularity or more thorough detail, where you can adopt something like the RAM model or a Turing machine model, and then you could pick that up. So when it comes to thinking about, oh, is this proven or not, the point I'm getting at is that there are many models of computation that have been proposed over the years, and I mean many. And I must stress that if you're really just unsure about this thing does have registers. So I must stress, it's not like this is some weird alien thing either. But I must stress that there are other models of computation that would not seem like something that would match a Turing machine that most certainly are also Turing equivalent. For example, you might ask, okay, well, if I introduce, say, randomization into my Turing machine, so-called probabilistic Turing machines, believe it or not, that does not actually introduce any new computational power to the Turing machine. It just functions a little differently. Just like my RAM model, it's more convenient for describing algorithms like on a physical computer, but it doesn't add any new computing power other than maybe some features involving complexity or maybe some other features, but it most certainly does not recognize more languages than a Turing machine does. Just like in the same vein, there also are other models of computation that describe all sorts of different kinds of computers. So for example, you may think of parallel computing. In parallel computing, you have multiple processors, right? Well, believe it or not, those multiple processors do not give you any special ability to recognize more languages than a Turing machine is capable of. The so-called, we have our recursive languages right now, and we also have the recursively enumerable languages. But you aren't going to get anything more out of parallel computing, for example. If you think of quantum computing, you may hear all about quantum computing and all the buzz around that. Not going to do anything new there either. The perk of quantum computing is its speed up. That's really what it's for. It's about its interesting implications for complexity, not necessarily its ability to describe languages. So what I'm saying is that there are many, many of these models that people have been looking at for years. And there's a whole area called computability theory where people have proposed all sorts of different models, ranging from things that look like machines to things that describe things like tiling, for example, to even things that look like more like a laptop. The point is that there's many of these models that have been shown to be equivalent to the Turing machine. So that means that if you think about your model, whether it be, for example, if you have a Harvard architecture-based machine or a von Neumann-based machine, there's going to be ways that I could use some Turing machine to describe that. It's going to be like I said, it's very, very interesting. And there's so much I could talk about here. This is why I want to encourage you to think about these things. So I want to just invite you to think about this. So just to be clear, so often the thesis itself serves as a useful means to describe computationally equivalent. When I say computationally equivalent, I'm talking about the languages they can describe. Computationally equivalent models of computation. Computation to Turing machines. So like I said, back in the day when Alonzo Church was thinking about this stuff, so with Turing and some other logicians, like they were thinking about different models. Turing's was what we call the Turing machine. But the idea here is that gives us a formal notion of what an algorithm is, assuming the Church-Turing thesis. But the Church-Turing thesis runs quite deep in the theory of computation. And like I said, there's many, many models of computation that are equivalent to the Turing machine or some conception of a Turing machine. So I'll be talking about one of those later on. But yes. Okay. Yeah, we're going to see this actually in the coming lectures, that reconciliations around the concept of infinity actually play a very weird role with this. We will most certainly be talking about that at some point. So this notion of infinity and how we can count actually does play an interesting relationship with what we can or can't compute, in the sense that when we talk about, well, we're going to talk about decidability. That's what's going to really creep in. But I will be showing you an example that there is no such Turing machine that will be able to actually capture all of the languages, which is going to be very strange to think about. So that if you believe the Church-Turing thesis, which almost every single person I could even tell you in the theoretical computer science community, they almost will tell you this because there's so many theorems that tell you that, oh yeah, everything's equivalent to this Turing machine. And every one of these describes a model of computation that matches something quite intuitive that you and I would use all the time when we think about computing. So, and I mean, like, it's a giant rabbit hole. Like, you could spend a whole course just thinking about things like pointer machines, register counter machines. I do not want to downplay how many of these models exist. It's a very deep hole. It's a very mature area of the field. And you could think about this as all sorts of different things, like functions in themselves to other things. So just think about it as, so just to summarize, just what I said earlier, to summarize, Turing machines are the standard model of what is computable. of what is computable, and how we formally define an algorithm. So if somebody asks you, and you're like talking to some computer scientist like me, they'll be like, oh, well, okay, okay, so when you talk about an algorithm, they might say, okay, well, so what is an algorithm? They'll probably tell you it's a Turing machine. That's what I'm trying to get at. Now, obviously, like I said, the Church-Turing Thesis tells us that there's all of these equivalent ways of talking about computation. So if you don't like just talking about it as a Turing machine, you can always pick up any computationally equivalent model of computation and describe an algorithm in that. And that's an algorithm too. Is that clear, everybody? So like when I tell you this, like you don't literally have to describe your algorithm as a Turing machine. You can describe it in any computationally equivalent model that is equivalent to a Turing machine. That's what the thesis is saying. Like it has very deep implications. So many that I will not talk about them all here. I want you to think about this. There's a lot of things that people think about when they talk about this thesis. There's a lot of different versions of the thesis as well. So just be warned. There are a lot of people out there that misconstrue this thesis. They say it says all sorts of other things, which actually it is actually that it's just a version of the Church-Turing thesis they're talking about. So for example, physicists have their own version of this. I'm just trying to stick to the most purest version of what the Church-Turing thesis tells us. But I want to invite you to think about this because this is a lot to lay on somebody. So are there any other questions? I thought that was a great question, by the way. Or are we all good to go? So I can start showing you what we could do with Turing machines. Do you want me to get into some Turing machine fun? If so, give me 2 thumbs up. Give me 2 thumbs up. Okay, great. So just because I've said this, everything I'm going to present to you, the spoiler is that every one of these things is going to be not adding any new computational power in terms of what we can recognize with languages. Now, just to reiterate, that doesn't necessarily mean that model cannot compute things faster, for example. So that's more of a complexity theoretic way of looking at it, which that is in fact going to be the case that different models have different, whoops, there goes my eraser. That was pretty epic, my apologies. So when we talk about going between different models of computation, each one may have its own description of how, say, for example, a move occurs. And different ones can have different time complexities. But the idea here is that when I go from one model to another model, there's going to be hopefully some connection between them from a complexity theoretic standpoint. And I haven't really talked about complexity theory a whole lot. I've just sometimes every once in a while reminded you, oh yeah, you could do this in big O of a different time. So depending how far we get, I'm going to bring up what we're going to say is the time complexity of a Turing machine. So I'm going to start working my way up to hopefully motivate this Church-Turing thesis by trying to throw more things at what a Turing machine is capable of. So we're going to talk about extensions and variants of Turing machines. So what I'm going to do is I'm going to try to buff up the Turing machine. I mean, I'm going to add more features to it. Kind of like what I did at the beginning of this course when I started talking about NFAs versus epsilon NFAs. That's what I'm going to try to do with this. And I'm going to show you, hey, look, all of these actually still are equivalent to Turing machines. Spoiler alert. So I want to start off by just mentioning a couple of things. Is that there's a variety of different things we can do to soup up or power up a Turing machine. Some examples I can tell you is that a couple ideas. So here's one idea that you could probably take advantage of, is that you can always encode code memory into the states. So that's one thing you can always do. So for example, you know how we always give names? Sometimes I give names to the states. Like I'll say, oh, it's like Q0. What you can do is you can also add a little bit of the interesting information about the input into the naming or encoding of the states themselves. So for example, you could instead encode it so that there's a tuple, some tuple that represents your state. So what you do is you just effectively add extra information in how you represent the states. So I don't want to go into the details of how this plays out, but this is just one idea I want to throw at you, is that you can always try to encode some more memory into the states. So very often when this happens, the number of states may go down, but the complexity of how I describe the states to you goes up. Likewise, if you ever want to find yourself speeding up the machine, which I won't really touch upon again a whole lot here, you could always try to incorporate more states that incorporate or hide all of the things that you're going to do with the tape itself within these states. So that's one idea you could do. Like I said, just encoding them like this as tuples, they're just still states, right? So it doesn't really do anything interesting for us. Another way you could do this is you can introduce so-called multiple tracks. So you could introduce so-called multiple tracks. And here's the idea. So you know how I have our tape, and I have the tape symbols, right? Well, what you can do, so remember we have our tape like this, and I have some symbols, like I don't know, I have like X and I have a bunch of blanks or something like that on the tape. And I have my tape head, right? What you could do instead is the following. What you can do is you can introduce what we call tape tracks. So these are called tracks. And each one of these is a tape cell. So you just read it vertically like this. So what you could do, for example, if I had this would be represented by X, Y, Z. So instead of having just my tape symbol being representing one symbol, I represent it actually as a tuple. So this is one thing you can always do to the Turing machine. And sometimes this actually does provide us some usefulness out of how we can encode the Turing machine. I'm going to show you an example depending on how much time we have later of this. So does everybody get the general idea of these two? So one idea I can always do is encode some more memory by just simply taking parts of the input and encoding that into the states as some tuple. Another way I can also go about this is by introducing, instead of just thinking of the tape symbols like one symbol, I can think of it as a tuple. And that tuple, each one of the positions is a track on here. So my my tape head here just points at all of those symbols on each track all at once. We're going to see a variant of something like this where I'm allowed to have it where I'm allowed multiple tape heads. So don't worry, I'm going to be getting to that. This point here is I'm just encoding multiple symbols onto one cell of the tape. So does everybody get the general gist of these two? I don't want to go into too much detail about each of these, but this one in particular is going to be useful for us a little later. So do you see how you could go about each of these? So you're just a matter of just encoding the Turing machine in a particular way. So these themselves just kind of buff up some of the features we have with our Turing machine, but they aren't themselves something that I would consider too interesting yet. So let me just want to say the following. Okay. So I'm going to say we want to see if we can add or modify features of Turing machines, and see if another model for the Turing machine, so this is some variant of one, has the same power. So it has the same power. So what do I mean by that? Just to be clear, that is, for any Turing machine M1, there is another machine, the supposed variant, another machine M2, where the language of M1 equals the language of M2. And vice versa, of course. So it means that they're going to accept the same languages. So here's the idea of how this is going to play out. So we are going to simulate one model using the other, so that a configuration of the original machine has a correspondence. That means that there's some series of moves that I can make that will match it. Correspondence of configurations of the simulated machine. You're going to see that what I mean by this in a moment. So the whole idea is that if there's some way I can take the moves of one of the machines and show you that there's an equivalent set of moves that I can make that arrives me at the same result for that given input, and this has to be true for all the inputs, then I could say that they're equivalent to each other. So the idea is I'm going to try simulating one of the models using the other. So does everybody get the general gist of the idea here? So I'm going to start off with the first thing that you could think of about souping up a Turing machine. So do you remember when I talked at the beginning about Turing machines, I told you, hey, look, we're going to assume that the tape head can go left or right. What did I tell you earlier? Like, what did I tell you that maybe would be nice? And I told you that there's some equivalent way of doing it with left and right. Does anybody remember? So remember, I told you, okay, we can have it so that we can move left or right. What was the third feature that I told you that, okay, well, maybe it'd be nice to have that, but I told you don't need it. It doesn't add any new power to the Turing machine. Does anybody remember? I want to introduce what we call, it starts with an S. I want to stay. I want to have an option where I could stay. Instead of going left and right, I want to have it so I can left, say, or go right. So the first thing I want to talk about are Turing machines with a stay option. So that means it's going to have this is a Turing machine where its transition function delta looks like this. Remember, I have a state, some tape symbol I am going to look at, and it gives me a state, some tape symbol to right, and then I'm going to have left, right? Remember, these are my directions, but I'm going to introduce a third one. I'm going to call this stay. And the stay option just means I don't move the head left or right. It just stays put. It stays in the same spot. So does everybody get the general gist of what the Turing machine with a stay option is? So it's just going to stay, so I have the ability to keep that head in one spot, as opposed to moving it left or right as well. Well, this is where, well, you would agree with me that any Turing machine most certainly is a Turing machine with the stay option, right? We just don't use it. So the question is, how do I take a Turing machine that does make use of these stay options? How do I turn that into a Turing machine without the stay option? That's really the question that we have. So I'm going to say, well, any Turing machine using left or right only is a Turing machine with a stay option. So that's one direction of that equivalency. So how can we simulate a Turing machine with a stay option? Well, suppose I tell you that M1, so say, how about we'll call, just for our sake, we'll call the Turing machine with the stay option, we'll call that, let's call that, because remember, I want to show you how I can simulate the Turing machine with the stay option. Whoops, I'm missing a Y for some reason. There we go. Thank you. What a weird day. What a weird day. So what I would like to do is I would like to take the Turing machine with the stay option. We'll call that M1. And I'm going to take the normal Turing machine that I have. I'm going to call that M2. So naturally, what I'm going to do is I'm going to try to show you how I can take M1 and make it into M2. Because doing M2 to M1 is really easy, right? I already just told you how you do it. You don't have to do anything. So, well, if delta is the transition function, of M1, where, suppose it's delta of Qi A, and this gives you the triple Qj B, and it has the stay option S like this. Remember, we don't really care about the left and rights. Those are okay. It's these stay options that are the problem for us. So those are the ones we need to simulate, really. But keep in mind, if you were to formally prove this, you would say, hey, look, well, all of the moves that are already based on left and right, we can use those in our regular Turing machine. However, there's these ones. These are the ones I have to do something a little bit more with. Then we can mimic this using this by using transition function delta prime of M2. So delta prime is going to be the one that we're building. So for all of the moves that are not the case that they have the stay option, in delta prime, you just make them equal to the ones that are in delta, just to be clear. It's just these ones with the stay option, I'm just showing you a construction for. Okay, so all you have to do is this. So watch this. So this might be the first thing you might try doing. And it actually works. Okay, if you have a stay option, remember, if you have the stay option, could somebody give, we only have about a minute here. Does anybody have any ideas of how I could simulate the stay option with just making moves left or right? Any ideas? You don't have to give me all the details. Just tell me what you think might be the best idea to try first? Yeah, you go back, you go back to the same state, but how do you do it? Because you got the first part, that's the other part. What do I have to do on that tape? So remember, if I'm staying, that means I don't move anywhere. So I need to simulate that with a series of moves. So that's the first part. But what I really want to know is what you do with the directions. What do you do with the directions? Yeah, exactly. That's exactly it. That's wonderful. That's exactly it. Yeah, you can go right, left, or left, right. So all I'm going to do is just describe that to you. So I'm going to introduce a brand new state. I'm going to call it JS. That's going to represent it's going to be a new intermediary step or state. Where I'm just going to write the same symbol I had before. Then I just need to add in one other one here. Now this is the part that you have to be careful about. So I'm going to have delta prime. So I'm going to go from this JS. So on state QJS. I want it for every symbol C so that I can go back to QJ. It'll write lambda. And then go back left. So if you're wondering what lambda is, it's just any symbol. So whatever symbol was there before, you just make sure you don't touch it, okay? That's what I'm saying. So you do this for every lambda in the tape symbol. So actually, I think this C is supposed to be lambda. Let me just put lambda back there. I think this is supposed to be lambda. Either way, you could think about it. If not, I'll definitely make the small correction. That's a typo on my end. My apologies. But yeah, all you do is just go right, then come back left. But we need a new state just to make sure that we can kind of get our way back. Does everybody see that? So to simulate the stay option, I just use 2 equivalent moves. That's all I need. So that's how I could simulate such a Turing machine. So when we come back next day, I'm going to give you more examples like these. And we're going to build and buff up our Turing machine until I basically get to something that's magical. Okay, so that being said, I want to say thank you very much and have yourself a beautiful day. I'll see you later.